All right, guys. So now we move on to the most important part of the lesson. So we are going to model with Poisson distribution, and this is the most important part, right? So the part that you need to really understand and where you get into the applications of actually using the Poisson distribution and where you see the differences between Poisson and binomial. Okay. Okay. So let's get into it. Okay. So you need to be able to recognize situations that can be modeled with the Poisson distribution. The Poisson distribution is used to model the number of times capital X that a particular event occurs within a given interval of time or space. So, guys, that's very important. So, this is, remember, discrete distribution, always capital X represents the number. Okay, whatever your event, it counts. It counts the number of times, that's capital X, within a given interval. That's very important. So, that's something that you didn't have in binomial. So you're counting this particular event occurring given a particular interval. Okay, that's very important. And that's what we use as our lambda value. Okay, so we'll go for some questions and let's see how to find this lambda and how to get the interval and how to get capital X. Okay, so let's go through the rules. So in order for the Poisson distribution to be a good model, the events must occur independently. That's a very important requirement. You see this in binomial as well, right? The events must occur independently. Like there should be no dependence. The events should occur singly. They should occur alone. Okay, not two events together at the same time. So it should occur singly in space or time. Okay. And then at a constant average. So guys, this is the main difference between Poisson and binomial, right? So here you have a constant average rate. Okay. There is a constant average rate. So that the mean number in an interval is proportional to the length of the interval. Okay. So whatever your event, it is happening at a certain rate. Okay. Like the phone calls per day. So you have 3 phone calls per day. That was the lambda line as an example. 3 phone calls per day. So that's the interval. The length of my interval is per day, 1 day. Okay. And the constant average is 3 calls. The length of the interval is 1 day. So if I change, so here they say the rate is proportional to the interval. What do we mean by proportional? So if I have 3 calls per day, so if I change the length of interval to 2 days, then my lambda becomes 6, right? Because 3 calls per day, so 3 times 2, 6 calls for 2 days. Okay. So basically, the rate is proportional to the interval. That's what they mean here. Okay, so let's actually go through some questions. Let's go through some questions. Let's see how to write capital X and go through these conditions. Okay, so mainly you need to see that there should be an interval and there should be a constant rate. Okay. Okay, so let's go through some questions in exercise 2C. So I'll go with the question number 2, starting with question number 2, right? Okay, so they say here a botanist suggests that the number of weeds growing in a field can be modeled by a Poisson distribution. Write down 2 conditions that must apply for this model to be suitable. Okay, so what are the conditions that must apply for this model to be suitable? So you can write any one of the two conditions that they've given here. There are 3 conditions that you need to satisfy in order to be a Poisson distribution. You can write any one of the 2 in within the context of the question. Okay, so the rules are it should be independent, should be singly in space or time, or there should be a constant average. So here I've said here, okay, so we're talking about the number of weeds growing in a field, right? It's modeled by a Poisson distribution. So you can see here I've written the assumption, okay, within the context of the question. Okay, so here I've written here weeds grow independently, right? So you can say the weeds grow independently of each other, okay? And then the weeds grow at a constant rate. Okay, so they grow at a constant rate. Okay, and such that the mean number in any area of the field is proportional, should be proportional, right? I mean, basically, bigger the area, the bigger the number of weeds. Okay, so anyway, you can try to match it with these statements. Okay, so the mean number in the interval is proportional. Okay, so let's move on to part B. Okay, so they say assuming this model, which means the Poisson model, and that weeds occur at a rate of 1.3 per square meter. Okay, so that's, what is this? 1.3 per square meter. This is your lambda. So you can see lambda is 1.3 per square meter. That's your length of your interval. That's the length of your interval. Your interval is a square meter. So 2 square meter, this doubles. 10 square meter, this becomes 10 times. Okay. That's how it is. So that's proportional. Okay. Find the probability that in a randomly chosen plot of 4 square meter, there will be fewer than 3 weeds. Okay. So how do we do this? First thing is define your random variable. Okay. Who is our random variable? Capital X. Define your random variable capital X very clearly. That is the key aspect here. So what is capital X here? So always capital X is going to be a number. Okay. It's going to be the number of whatever your event. So what's our event? The weeds. Okay. So here my event is the number of weeds growing in. In this case, I want, here they say in the question for 4 square meters. Can you see? Find the probability in a randomly chosen plot of 4 square meter, there will be fewer than 3 weeds. Okay, so before I move on to here, my chosen plot is 4 square meter. So I want that capital X be the number of weeds growing in 4 square meter. So guys, now let's let's model the Poisson distribution. How do you model it? X follows a Poisson distribution. Now the lambda is 1.3 per square meter, right? 1.3 per square meter. But here I'm working with 4 square meters. So because I'm working with 4 square meters, what do you have to do here? You need to get the lambda according to the length of the interval. So my capital X is defined for an interval of 4 square meters. So you had to fix lambda for 4 square meter, which means 1.3 should be multiplied by 4. So 1.3 times 4 is 5.2. Okay, that's very important. Okay, according to your capital X, the length of interval, you have to have your lambda value adjusted. Okay. Right, so here my capital X follows a Poisson distribution with mean 5.2. And what do I want? I want there to be fewer than 3 weeds. So capital X is the number of weeds, and I want that to be fewer than 3. So guys, this need to realize that fewer than 3 means less than 3, right? So it should be lower than, smaller than 3, not equal to 3, but fewer than 3, right? So these are some basic terminologies. You learn this in the chapter 1, right? So fewer than, greater than, at least, at most, all those words were there in chapter 1. Okay, so you should be able to realize fewer than 3 means X is less than 3. X is less than 3 is actually X is less than or equal to 2, right? So I've written here X is 0, X is 1, X is 2, but this is basically, in other words, X is less than or equal to 2. So you can get this probability directly. I think we can't get it directly. Why? Because the table at the cumulative distribution table has only certain lambda values, right? It only has lambda values with the multiples of ending with 5s and 0s. The lambdas where the final digit is a 0 or a 5. Okay, so 5.2 is not there in that table, which means you'll have to do it manually. Okay, which means you'll have to do it manually. So going for X less than or equal to with the table is not going to help you. Okay, so because of that, you can find it by using the calculator. Okay, you can find it by using the calculator. So you can see I've written all the individual probabilities individually for each one, and I've got the answer. Okay, so that should be understandable, right? Because now you know from the previous exercise how to use these equations, right? So this part should be okay. All right, so I'll move on to part C. They say the probability that in a randomly chosen plot of 5 square meters, there will be more than 8 weeds. Okay, can you see what's happening now? Can you see? So they are now changing the length of the interval, right? Part B, the length of the interval was 4 square meter. But now in part C, the length of the interval is changing. So in this context, okay, my advice to you is whenever they change the length of the interval, you introduce a new random variable. Now, capital X was for the number of weeds growing in 4 square meters, right? So now, since they're changing it to 5 square meters, in part C, introduce a new variable, capital Y. Okay, I'm introducing another variable, capital Y. And capital Y is the number of weeds growing in 5 square meters. Can you see? Introduce a new variable Y. And Y follows the Poisson distribution. And what's the mean? So for 1 square meter, mean was 1.3. For 5 square meters, it should be 1.3 into 5. Okay, so 1.3 into 5 is 6.5. All right. So Y follows a Poisson distribution with mean 6.5. Okay, that's the first thing you do. You read the question, you get the length of the interval, and you get the lambda value. You get the lambda value. You define your random variable with respect to the length of the interval and get the lambda value. That's the first thing to do. So after you do that, now go back to the question. What is the probability we need to find now? The probability in a chosen plot of 5 square meter, there will be more than 8 feet. So I need the probability there is more than 8. So more than 8 means what? I need the probability that y is bigger than 8. Can you see y is greater than 8? Okay, so y is greater than 8. Guys, you know the conversion. So I've shown you this conversion many times now in the previous exercise as well. So 1 minus probability greater than means 1 minus y is less than or equal to 8. And guys, in this case, we can use the table because the lambda value 6.5 is there in the table. 6.5 lambda value is there in the table. You can see it's ending from 5. This is there in the table. So this value can be found easily. Okay, so for 8, okay, go to the the lambda column 6.5, simple x value 8, and you will find this value 0.7916. 1 minus that is 0.2084, which is the answer. All right, guys, so that's the answer. All right, guys, so next I'll move on to question number 4. So I hope you guys are getting a good idea about how the Poisson distribution works now. Okay, so try to get the idea. Okay, so here they say a call center agent handles telephone calls at a rate of 15 per hour. So can you see? There's a rate, and he handles telephone calls at a rate of 15 phone calls every single hour. Okay. Find the probability that in a randomly selected 20-minute interval, okay, the agent handles exactly 4 calls, more than 8 calls. So guys, the rate is given to you at the rate is lambda is described as 15 per hour. But the thing is, the question asks you in a randomly selected 20-minute interval. Okay, so the question, the probabilities you need to find here are for 20-minute interval. So because of that, when you're defining your random variable, capital X, you define it on the 20-minute interval. So number of calls in a 20-minute interval. Okay, so that's how you need to define your capital X, number of calls in a 20-minute interval. And you can see you need to get your lambda value now. So it's 15 per hour, right? 15 per hour means 15 per 60 minutes. That's in 60 minutes. So I need to get in 20 minutes. So for 20 minutes, I should divide this guy by 60 divided by 3. 15 divided by 3, right? Because I'm dividing both sides by the intervals are proportional. So 60 divided by 3 is 20 minutes and 15 divided by 3 is 5. And that's how I have got here. It follows Poisson distribution with lambda 5. Okay, so that's how I got my lambda value. Okay, so I need to find now in part 1 the probability that there are exactly 4 calls, which means capital X, the number of calls in a 20-minute interval, is equal to 4. Right, guys? So probability X equal to 4. This, of course, you can do it directly also. Probability X equals 4 is e to the power minus lambda. Lambda is 5 into lambda to the power x. X is 4 divided by 4 factorial. This can be used directly, right? Or the other option is like what I've done here. You can see x is less than or equal to 4. When I subtract with x is less than or equal to 3, you need to realize that I'm remaining with directly just the probability of x equals 4, right? Because x is less than or equal to 4 means 0, 1, 2, 3, 4. X less than or equal to 3 is 0, 1, 2, 3. When you subtract, only the probability x equals 4 is remaining. Okay, so that's one way. That is if you are using the cumulative distribution table, this technique. Or this technique is where you can just use the calculator. Okay, and you get the answer in one go. 0.1755 should be the answer to 4 dp. Okay, regardless whether you use the table or the calculator, you should end up getting the same answer. Okay. Okay, then part 2, under the same 20-minute interval, more than 8 calls. So guys, probability x is more than 8. So x is greater than 8. Right? So you know how to convert. I've given the conversion many times now. X greater than 8, x greater than 8 is 1 minus probability x is less than or equal to 8. Okay, so then that's this value. You can get it from the table by going to the lambda value 5. go to the lambda value 5 and go to the simple x value 8 and you get the value 0 0.9319. 1 minus 0 0.9319, 0 0.0681. So I showed you guys how to use this table, right? So if I show you just quickly, lambda value is 5, simple x value is 8. Here, lambda value is 5, simple x value is 8. Right, so you can see here 0 0.9319. Can you see? 0 0.9319. This value you can get it from the table. I hope you guys saw it. Let me show it again. Okay, so here lambda value 5, x value 8. This is the x value 8. Go to the respective value 0 0.9319. So this value is what I have used in the calculation. All right. Okay, that's what I've written here, and this is the answer. Okay. Okay, moving on to part B, find the probability that in a randomly selected 30-minute interval. Okay, so you can see what's happened here. The interval has changed. It's a 30-minute interval now. So remember, whenever the interval changes, introduce a new random variable. Whenever the interval changes, introduce a new random variable, okay, with respect to that new interval. So it's a 30-minute interval, which means I'm going to introduce random variable y, which gives me the number of calls in a 30-minute interval. Okay, that's 30-minute interval. And then in a 30-minute interval, so for 60 minutes, it's 15 calls per 60 minutes. So 30 minutes is dividing by 2, right? 30 minutes is dividing by 2. So dividing by 2, 15 divided by 2, it's 7.5 in 30-minute interval, right? So here your lambda value is 7.5. Okay, so that's number 1. And what do I need to find now under that lambda value? At least 6 calls. So guys, this is important. At least 6 means, so again, I told you how to read these at least, at most. These things are, it's important that you should be able to convert them in terms of words and the table. There is a table given to you about this at least, at most. It's given to you in chapter 1 in the binomial distribution lesson. There's a table that's given that describes all these phrases and how to convert them to these kinds of probabilities. So you guys need to make sure you know that very well, right? So refer that table if you do not know. So anyway, at least 6 means 6 or more than 6. Right? At least 6 means 6 or more than 6. That's why I've written here y is greater than or equal to 6. So guys, the conversion table I've given you, right? So this is the conversion here. So greater than 6 means, greater than or equal 6 means 1 minus probability x is less than or equal to 6 minus 1. Okay, so that's again something we learned in the previous chapter. So y less than or equal 5, again, what do you do to get this probability? Go to the Poisson cumulative distribution, go to lambda value of 7.5 column and go to simple x value 5 and you will get this value of 0 0.2414. Subtract and you get 0 0.7586. Okay. And then moving on to the very last part, Roman number 2, they say no more than 10 calls. So no more than 10 calls means you can't exceed 10. It should be less than or equal to 10. Okay, so immediately you should be able to convert those phrases into these statements, into these kinds of expressions. Okay, so no more than 10 means it should be 10 or lower than 10. Okay, so those phrases are explained in the table that I mentioned in chapter 1. Okay. So no more than 10 means y is less than or equal to 10. And you know, this is the format that is directly useful for us because I can use this format directly on the cumulative distribution table. So go to the table and go to lambda 7.5, go to simple x value of 10. Okay. So lambda 7.5. Here lambda 7.5, this value is 10. 0 0.8622. All right. That's what I have here, 0 0.862. All right, guys. So this should be. I hope now the idea of Poisson distribution has become clearer to you. The concept of the interval and how the interval is proportional, and how the lambda, the rate, is proportional to the interval. Right. So with these 2 questions, I believe that you might have a better understanding about the Poisson distribution now. Okay. Okay, guys. So now let's move on to some more deeper questions. Okay, where things get more uh, okay, where you need to understand a little bit extra. Okay, so let's see how things differ here. Okay, so basically part A and B is exactly the same as we did before. Let's go through them first. Okay, so flaws or mistakes occur at random in a particular type of material at a mean rate of 1.5 per 50 meters. So can you see the interval? The interval is 50 meters. So every 50 meters, the flaws are occurring. You have 1.5 flaws. Okay, so if it's 100 meters, then it's 1.5 times 2, right? So basically here the rate is given to you per 50 meter. Every 50 meter, you have 1.5 flaws. Okay. Find the probability that in a randomly chosen 50-meter length of this material, there will be exactly 3 flaws. Okay, so you can see we are working with the 50-meter length. So then, because we are working with the 50-meter length, let's define our random variable capital X as the number of flaws in a 50-meter interval. Okay, so that's what you need to do first. You define your interval. Okay, you define your random variable with respect to the interval. Okay, so that's done. And then let's okay, so then what do we have here? We have X follows a Poisson distribution with the lambda value. The rate is 1.5, right? 1.5 flaws. All right. So I want to find the probability that it is exactly 3 flaws. X is equal to 3. Okay. So you can find by using the formula for Poisson distribution, e to the power minus lambda, lambda to the power x over x factorial. Lambda is 1.5, x simple x is 3. Substitute the values. You can use the calculator and get the answer 0.1255 correct to 4 decimal places. Okay. Okay. So that's the answer for part A. We'll move on to part B. This material is sold in rolls of length 200 meters. Okay. So find the probability that a single roll has fewer than 4 flaws. Okay, a single roll is 200 meters, right, guys? So what's the first thing you do here? You know the flaws are occurring at a rate of 1.5 per 50 meters. First thing is let's define a new random variable for 200 meters. So I'll get y. Y is the number of flaws in a 200-meter interval, right? 200 length of material. Okay, and then y follows a Poisson distribution. So guys, 50 times 4 is 200. So therefore 1.5 times 4 is what you need to get the lambda here, which is 6. Okay, so I need to find the probability that a single roll has fewer than 4 flaws. So here, y fewer than means less than 4. So less than 4, you know, is what? It's basically less than or equal to 3 in discrete distribution. So that 0 point, I mean, you can go to the Poisson distribution, cumulative distribution table, go to lambda value 6, go to simple x value 3, and you get this answer. Okay, I think that part you can do it, right? 0.1512, you can get the answer from the cumulative distribution table. Make sure you go to the correct lambda column and the simple x value 3, and you should get this, okay? Okay, so that should be easy, and that is done. Let's move on to part C. Okay, so guys, this is where things get a little bit tricky, okay? They say Priya buys 5 rolls of this material. Okay. So 5 rolls, you know, a single roll is 200 meters. She buys 5 rolls of the material. Find the probability that at least 2 of these rolls will have fewer than 4 flaws. Okay, guys. So this, you can see it's 5 marks and it might trip you up a little bit because for one reason, we are going to involve a binomial distribution here, guys. Okay, so you might be wondering, okay, how is a binomial distribution coming here? Okay, look, so we are, in a binomial distribution, you have a fixed number of trials, and your random variable gives you the number of successes, right? So here, I'm going to define my successes as the number of rows that have fewer than 4 flaws, because that's what I want to find, right? Okay, you are supposed to find the probability that at least 2 of the 5, you have 5 trials here. There are 5 rows. So I want at least 2 of these 5. Okay, at least 2. So it could be 2 or 3 or 4 or 5, because at least 2 means 2 or more than 2, right? Okay, so I want at least 2, okay, 2 or more of these rows to have fewer than 4 flaws. You guys, so don't get overwhelmed by these at least and fewer than, okay? Just try to break it down, okay? So fewer than 4 flaws. Okay, so what I'm going to do here is, okay, I have 5 roles, which is my number of trials, and I'm going to consider the event or a successful event where if I have a role with fewer than 4 flaws, that's a success. Okay, so here you can see I've given my random variable. So here I'm going for another variable, capital A. Okay, and here I'm defining capital A to be the number of rows with fewer than 4 flaws. Okay, basically using whatever the information they gave me in the question. So A is the number of rows that have fewer than 4 flaws. And then you can see here A follows a binomial distribution. Guys, look, number of trials. I know I have 5 rows. So there are 5 rows, and what's the probability of success? The probability of success is, I mean, a role with fewer than 4 flaws, right? I mean, I know A is my event. Okay, in binomial, we write here N is the number of trials, P is the probability of success of that event. Now, this is my event. The event that I'm defining is where we have a role with fewer than 4 flaws. So what's the probability of having a role with fewer than 4 flaws? Didn't we find it in part B? Because in part B, we considered a single 200-meter roll, and we found the probability of having fewer than 4 flaws in a single roll is 0.1512, right? This we found in part B, the probability that a single roll of 200-meter has fewer than 4 flaws. So guys, over here in this question, okay, I have a fixed number of trials, that's 5. I have 5 rows, and I'm going to consider this a successful event where the event is defined as a role. If I have a role with fewer than 4 flaws, that's a successful event. Okay, so the probability of having a successful event, this probability where I have fewer than 4 flaws is 0.1512. So basically, guys, if probability capital A is 1, what does that mean? It means out of the 5 rows, there is only 1 row with fewer than 4 flaws. Do you see? Probability capital A equal 1 means out of the 5 rows, there is only 1 row with fewer than 4 flaws. If I write probability capital A is 2, what does it mean? It means out of the 5 rows, there are only 2 rows with fewer than 4 flaws. Do you see what's going on? This is really important. And this is something that you will be tested in the exam. You'll see this a lot in the exam. Okay, where at the end of the Poisson distribution question, you have a binomial part coming into it as well. Okay, so here it's just taking the Poisson probability into a binomial distribution question. Only the probability is needed here. Okay. So you need to realize the way you define your random variable is really powerful, and that explains many things. Okay, so it's really important. You should be able to define this very clearly. Okay. So capital A is the number of rows with fewer than 4 flaws. So what do I need? I need to find the probability that at least 2 of these rows has fewer than. So at least 2. I need to find the probability that there are at least 2 with this condition. So at least 2 means what, guys? At least 2 means A is greater than or equal to. This is what I need, right? At least 2 means A is greater than or equal to 2. So A is greater than or equal to, you guys know how to convert it. It's 1 minus probability A is less than 2. Less than 2 means it's less than or equal to 1. Right, guys? And then less than or equal to 1 means A is 0 and A is 1. Right, guys? And then this is binomial. So how do you work with binomial? Probability capital X equals simple x, NCX, p to the power x, 1 minus p to the power n minus x. This is from chapter 1. Right? So here my n is 5. And you can input the p-value 0.1512. I just use this formula. For A is 0 and this is for A is 1. And this is all in the calculator. You can type it in the calculator to get this answer. Okay, so this is a tricky question. Okay, this is a tricky question, but it's something that you need to master the art of. Okay. Okay, guys, so let's try another one. Question number 11. They say a company produces chocolate chip biscuits. The number of chocolate chips per biscuit has a Poisson distribution with mean 5. Can you see? So per biscuit, can you see? You have to identify an interval per biscuit. That's the interval. The number of chocolate chips, or the mean, the lambda value is 5. Okay, so they say find the probability that one of these biscuits, again, so you're in the same range, the same lambda then, okay, because it's per biscuit, so you're working with one biscuit, okay. Find the probability that one of these biscuits selected at random contains fewer than 3 chocolate chips. Okay. So what do you do? First, describe your random variable with respect to the interval. The interval is 1 biscuit. Okay, so a capital X is the number of chocolate chips per biscuit. Okay, in 1 biscuit. And then, it follows a Poisson distribution with mean 5, because we know there are 5 chips per biscuit. All right. And then we need to find the probability it contains fewer than 3. So X is less than 3. That's the probability I need to find. X less than 3 is X is less than or equal to 2. So X is less than or equal to, how do you get the probability? Go to the Poisson cumulative distribution function table. Lambda value 5, simple X value 2. And you get this answer 0.1247. Okay. So that answer you can get from the table. Okay. So that should be fine, right? I'll move on to part B. Okay. A packet contains 6 of these biscuits selected at random. So guys, this is the one you have to be careful again. The one where it involves the part with binomial, right? So look, a packet contains 6 of these biscuits selected at random. Find the probability that exactly half of the biscuit, which means out of 6, you want to find the probability 3 of the biscuit contain fewer than 3 chocolate chips. So guys, you need to realize, first of all, in this question, there's nothing to do with Poisson distribution here. Like there's no mention of a changing interval. There's nothing like that. So the packet has 6 biscuits and you need to find the probability half of the biscuits are having fewer than 3 chocolate chips. So guys, we know in a single biscuit, the probability of having fewer than 3 chocolate chips is 0.1247. Can you see? That we know. So what you need to do here is, okay, you have 6 biscuits, which means 6 is the number of trials, and define the probability of success as having a biscuit with fewer than 3 chocolate chips. That's the event, or that's the successful event now. Okay, where a biscuit having fewer than 3 chocolate chips is a successful event. So here I'm defining Y to be the number of biscuits with fewer than 3 chocolate chips. And Y follows a binomial distribution. So we have 6 trials because there are 6 biscuits, and the probability of having fewer than 3 chips, 3 chocolate chips in a biscuit is 0.1247. So I need to find the probability that exactly half of the biscuit, which means that I need to find the probability Y is half of 6 is exactly Y is equal to 3. So this is the binomial distribution NCX p to the power x 1 minus p to the power n minus x. So substitute the p value and the n value, and you can type this value in the calculator and you can get the answer. That's very straightforward. All right, guys. So I hope that you are now able to understand how the binomial distribution questions, how binomial can be used inside the Poisson distribution question. Okay, it's just the Poisson probability is used, but in order to use binomial, they will introduce a fixed number of trials. And then you have to define your successful event, and the probability you'll have to use the probability you calculate from the Poisson distribution, and then calculate the probability of success for the binomial event. Okay, so that's how that works. All right, guys. So next I'll move on to question number 13. Okay, so they say, on a typical summer day, a boat company hires out rowing boats at a rate of 9 per hour. Okay, so again, you can see the rate 9 boats per hour. That per hour, the interval is an hour. Okay, lambda is 9, so 9 boats at every hour. Okay, so find the probability of hiring out at least 6 boats in a randomly selected 30-minute period. Okay, so guys, the interval changes to 30 minutes. So define your random variable capital X for 30 minutes. So number of boats hired in a 30-minute interval. Okay, in 30-minute interval, in a 30-minute period. Okay, and then you can see for 1 hour, if it's 9, for 30 minutes, it's half of 9, which is 4.5. So probability of at least 6 means what? 6 or more. So probability X is greater than or equal 6. That's the meaning of at least, right? So how do I get the probability? In order to calculate the probabilities, I need to convert it to the less than or equal probabilities, right? So again, using the conversion table. So this conversion, when it's greater than or equal, it's 1 minus probability less than or equal to that value minus 1. Okay, so here less than or equal to 6 minus 1, which is 5. So go to the Poisson table, lambda 4.5, simple X value 5. You can get this value 0.7029, and the answer is 0.2971. Okay. Yeah, 0.2971. That should be okay, right? So these values, you should be able to use the table now. I've shown that to you many times, how to use the table, how to find the probabilities. So this should be okay, right, guys? Okay, so I'll move on to part B. The company has 8 boats and decides to hire them out for 20-minute period. Okay, so guys, can you see now what's happening? They are kind of setting on and kind of like an upper bound here. Okay, the company has 8 boats and decides to hire them out for 20-minute periods. Okay, so 20-minute period. Again, you can see the lambda is also the interval changes. The lambda will change because you are going for 20-minute periods now. Okay, so for sure that the probability of running out of boats is less than 1%. So guys, what do you mean by running out of boats? What do you mean by running out of boats? So every 20 minutes, okay, they're only renting out for 20 minutes. So which means the boat comes back to them and every boat they rent out comes back to them at the end of 20 minutes. So then there are only 8 boats. So how do you run out? How do you run out? You only run out when you have now, let's define our variable. Now we have a 20-minute period, right? So let's define, because it's 20 minutes, I'm going to define a new variable y. So what is y? Y is the number of boats hired in 20 minutes. The number of boats hired in 20-minute interval. Okay, a 20-minute period. Okay, so how do I run out? So basically I run out if the number of boats that I need to hire is what? I only have 8 boats. So I'm only going to run out of boats if I'm going to get boats that I need to hire. The number of boats I need to hire will exceed 8, right? That means I get more than 8 orders. Okay, so I only have 8 boats. The probability that I'm going to run out of boats is if I have more than 8, only if it's more than 8. Do you see? So this is very important. The probability if the number of boats hired in 20 minutes is more than 8. So where I get more than 8 requests, that is when I run out, right? Okay, so that's where you get y more than 8. And guys, what about this 3 here, the lambda? So you can see it's a 20-minute period, right, guys? So per hour is 60 minutes. So lambda is 9 for 60-minute interval. So I should divide 60 by 3, right? To get 20 minutes, so 20-minute interval, 9 divided. So I have 3. The number of boats. My lambda value is 3 for a 20-minute interval. Okay, so that's the lambda value here. Okay, so running out of boats is if I have more than 8 requests. More than 8 boats needs to be hired in a 20-minute period means I am running out of boats. That's the probability I have to find. So let's find the probability y greater than 8 is 1 minus probability y less than or equal 8. So how do you get y less than or equal 8? Lambda value 3, simple x value 8. You can get it from the Poisson cumulative distribution function table. The value here in the table is 0.9962. You know now how to read the table. Okay. And then subtract that from 1 because it's 1 minus here. And then you get 0.0038, which when you convert to a percentage is 0.38%, which is smaller than 1%. That's what you need to show, right? They want you to show that the probability of running out of board is less than 1%, right? 0.38 is smaller than 1%. 0.38% is smaller than 1%. So that's exactly what we wanted to show. Okay, guys, so that's what they wanted us to show, and we showed that. All right. I hope that part is clear. Okay, so moving on to the part C, the last part. Find the number of boats that the company should have in order to be 99% sure of meeting all demands if the hiring period is extended to 30 minutes. Okay. So again, for each question, first thing is define the random variable with respect to the interval. What's the interval now? We are again working with a 30-minute interval. So if you're working with a 30-minute interval, you don't have to define a new random variable because we already have for the 30-minute interval, we have capital X. Right? So we can work with capital X. Are you with me? Okay, you don't have to give another variable. Don't go for Z or A or don't give any new variable because already for 30 minutes, we already have defined capital X for 30-minute interval. So work with capital X for 30 minutes. Okay, even if it's in a lower part. Okay, you can work with capital X because we defined it for 30-minute period. Okay, so now what's the question? You had to find the number of boats that the company should have in order to be 99% sure of meeting all demands. So they need to meet all the demands and they need to be 99% sure of meeting the demand. If the when the hiring period is 30 minutes, okay. If the hiring period is 30 minutes, we know first of all our lambda value is 4.5. Are you with me? When the hiring period is 30 minutes, lambda is 4.5. I'm working with random variable x. So then what do I want? I want to meet all the demands, right? So I want to meet all the demands means what? Now, I need to, the number of boards. So let's say during this 30-minute period, in order to meet the demand, I need, let's say we need n number of boards. The number of boards we need is n. Okay, in order to meet the demands, let's say we need an n number of boards. That's what they ask. What is this n number? How many boards do we need? Okay, what is the n number of boards that we need to meet the demand? Okay, so in order to meet the demand means what? The number of boards that I'm hiring, in order to meet the demand, the number of boards that we hire, what do you think it should happen? Should x be greater than n, or should x be like, less than or equal n? What do you think? I need to meet the demand, right? If x is bigger than n, then you can see that I'm again running out of boards. That's what happened here. We had 8 boards, and when we had more than 8 boards needed to be hired, we ran out of boards. So here I have n boards. If I have the number of boards that I'm hiring is bigger than n, then I'm running out of boards. But if I need to meet all the demands, then my x needs to be, the number of boards I'm hiring should be less than or equal to n. I can go until n. So if I can have this condition, then I'm meeting the demand, which means I can give boards to all the demands that I'm getting. I can satisfy the demand. So this is what we need, right? If this is the case, then we run out. Here we run out. That's what happened here. Okay, so here I want the probability x is less than or equal n is where we meet the demand. And this, what is the case? They say find the number of boards the company should have in order to be 99% sure. So I need to be 99% sure of meeting the demand. Can you see? So the probability, this probability, I need it to be what? The probability. Okay, so I need this probability to be, I need this. Can you see here? So it needs to be more than, greater than or equal to 99. It can't be less than, right? You don't write equal here also. So I need to be 99% sure. So which means 99% or more. Okay, the meaning of 99% sure means, okay, 99%, it can't be lower than that. But my probability should be 99% or more. So I need to be sure, 99% sure, percent or more. Because more means it's better, right? More means it's better. So here, this is the probability of meeting the demand. I should be 99% sure of meeting the demand, which means 99% or more is also better, because then I'm going for a higher probability. Right there. So this is the crucial statement. You should be able to read this particular question and come out with this. And this is what you need. If you can write this part out, getting n is not difficult, because we've done questions like this in part in exercise 2B, right? In 2B, we did questions where we found these kinds of n values. Getting n is easy, but writing this expression is what's difficult. Okay, read the question and write in the expression. 99% sure means you need to realize it should be greater than or equal 99. That's very critical. Okay, this is greater than or equal 99. Okay, and then you know what we do here, x less than or equal n means I'm directly in the format of my table, right? Directly in the format of the table. I don't have anything to convert. So I need the first probability. I need the n values where I exceed the smallest number of boards, right? I find the number of boards. Okay, so I can get the smallest number of boards here. For x, capital X, the lambda value is 4.5, right? Yeah, for capital X, the lambda is 4.5. So let's go to the table. Let's go to lambda 4.5 and see where we exceed 0.99. Okay, so where do we exceed 0.99 for 4.5? The first one is this one, right? This is the first guy that exceeds 0.99. 0.9829 is small. 0.9933, this is the first n value that exceeds 0.99. So 10, 11, 12, all of these guys are exceeding. Okay. So, so what we need to do here is, so you can see the first guy is 10. So x is less than or equal 10. So anything more than 10. Do you guys see? So n actually can here be, okay. So you can have 10 or more than 10 boards. So basically what I need is minimum, I need 10 boards. Do you guys see why I'm saying 10 or more than 10 boards? This I explained this concept in exercise 2B in the previous video, right? Where we were doing some questions in the 2B exercise and I showed you how these kinds of values were found. So you saw that in the table that not only n value 10 satisfies, and here when x is less than or equal 11 also, the probability exceeds 0.9 and x is less than or equal 12 also exceeds 0.99. Okay, so in order for the company to work, we can give the smallest number of boards they need. So they need at least 10 boards. Do you see? Okay, so it needs that they need at least 10 boards to be 99% sure of fulfilling the entire demand. All right, guys, that's the process here. All right, guys. So now I'll do the last question in this exercise in order for you to understand this really well. So we'll do one more question. Question number 14, breakdowns on a particular machine occur at a rate of 1.5 per week. So guys, can you see the interval is per week? The rate is 1.5 breakdown. Okay, so breakdowns, lambda value is for the breakdowns and the interval is per week. Find the probability that no more than 2 breakdown occurs in a randomly chosen week. Okay, so I'm still going with the week here, which means we define capital X, our random variable, number of breakdowns in a week. Okay, so X follows a Poisson distribution with lambda value 1.5. I want the probability no more than 2 means less than or equal to 2. Do you agree? No more than 2 means less than or equal to 2. Okay, so that again, really easy. You go to the Poisson table, go to lambda 1.5, go to simple X value 2, and you can immediately get the answer. So this is not hard, right? We'll move on to part B. Find the probability of at least 5 breakdowns in a randomly chosen 2-week period. So 2-week period means what? You're changing the length of your interval. I told you if you're changing the length of the interval, change the variable and change the interval and write the new Poisson distribution. So y is my new variable, which represents the number of breakdowns in 2 weeks. So y follows the Poisson distribution 1.5 times 2, right? Because 1.5 per week, 2 weeks means 1.5 times 2. That's 3. Okay. So what do I want? The probability of at least 5 breakdowns. At least 5 breakdowns means greater than or equal to 5, right? Greater than or equal to 5. So you know the conversion. I've shown this to you now plenty of times. Greater than or equal to 5 is 1 minus probability y is less than or equal to 4, right? And then this again, you go to the lambda value 3 in the Poisson table, simple X value 4, and you get this value 1 minus that, and you get this answer. So I don't think that's difficult, right? We did many questions with similar to this. I've shown you how to use the table, right? So they should be understandable, hopefully. Okay, this part is done. So let's now move to the main part. Part C is the one that I really want you guys to understand, and the one that you need to basically write the expression. The most important thing in part C is writing down the correct expression. Okay, so let's read. The maintenance firm. Let's take it here. Okay. A maintenance firm agrees to repair breakdowns over a 6-week period. Okay. Can you see there's a 6-week period now. The firm will give a full refund if there are more than n breakdowns in a 6-week period. The firm wants the probability of having to pay a refund to be 5% or less. Find the smallest possible value of n. So guys, all you have to do is convert these statements, this entire statement, you have to break it down into mathematical expressions now. Okay, what's the first thing to do? The first thing I do is, okay, I'm going to define the Poisson distribution for the 6-week period. Okay. I'm going to define the Poisson distribution for the 6-week period. So I'm going to define, okay, normally we don't use capital Z. Okay, capital Z, now you can see I use capital X, Y, and then I don't use capital Z because normally capital Z is used to work with standard normal distributions. Okay, so I'm using capital A. Okay, because it's customary, it's normal to use. I mean, we don't use capital Z for random variables other than standard normal. Okay, so I'm going for capital A. Okay, use any other capital letter you want other than Z. Okay, so what capital A? The number of breakdowns in 6 weeks. Can you see? I'm giving 6 weeks now. And for 1 week, it's 1.5. 6 week is 1.5 times 6, which is 9. Okay, now guys, let's try to write down the statement. Okay, what do they want? the firm will give a full refund if there are more than n breakdowns in a 6-week period. Okay, so when do they give the refund? If there are more than n breakdown. Okay, so capital A is the number of breakdowns. So the refund is happening if A is more than n, if A is greater than n, right? Can you see? If A is greater than n, then this is the refund. This is when you get the refund. Okay, if the number of breakdowns is greater than n, then they get a refund. The firm wants the probability. Now, this is the probability of getting a refund, the probability of having to pay a refund. This is the probability, right? Because if there are more than n breakdown in the 6-week period, then you have to, then the probability, so this is the probability of getting the refund. Okay, they want this probability to be 5% or less. So 5% or less, so less than or equal 5%. This probability should be less than or equal 5%. That's it, guys. Okay, so after writing this statement, the rest of the thing is easy, right? And the rest of the thing is where we do the conversion, and same as we did in exercise 2B at the end of the previous video. So I showed you guys how to work with these, right? A greater than n is 1 minus probability A less than or equal n. You let this part be, I'm not doing any change here. Less than is here, the 5% is here. And then I'm switching minus probability A less than or equal n goes to the other side. The 0.05 comes here. And then I have 0.95 here, less than or equal, and here probability A less than or equal n. I'm just going to rewrite this exact same sum here. So it's probability A less than or equal n. The mouth is open towards this guy, right? Here, the mouth is open towards the probability. So greater than or equal 0.95. Can you see? So when you are in this format, you can use the cumulative distribution table. Use the cumulative distribution table to see where you exceed, where you are equal or exceeding 0.95. So what's our lambda value? Lambda value is 9 now. Remember, go through the correct lambda value, okay? Because now capital A random variable is defined for lambda value of 9. So you go for lambda value of 9 and see where you have 0.95 or more. So here's my lambda value of 9. Okay, so here's my lambda value of 9. So where do I exceed 0.95? So this is the first one where I exceed 0.95, right? At 14. Do you see? So this is the first one. This is the first one that exceeds 14. The rest of them exceed 14 as well, and 0.95 as well, but 14 simple exceeds 14 is the first one that exceeds 0.95. That's it, guys. The smallest value, the smallest n value is 14, because here 15, 16, they also exceed 0.95. Okay, but I want the smallest is 14. Okay, the smallest possible value of n is 14. Thank you, guys. So I hope this part is now clear with everyone, right? So this is the main idea behind the Poisson distribution. Okay.